Hello guys, welcome to our third lecture on photonic devices. In this lecture, we're going to talk about the classification of solids in metals, insulators, and semiconductors. And we are also going to introduce the band structure, which is a graph of the energy as a function of wave vector k. So solids can be classified into three general categories: metals, semiconductors, and insulators. And this is going to depend on the band diagram or the band structure of these types of solids. Okay, so let's recall some concepts that we saw at the end of the last lecture. So in classifying these different types of solid, the valence band and the conduction band play an important role in this classification. The valence band is the highest energy band whose states are fully occupied. So the highest band, which is completely full, is occupied by electrons at a temperature of 0 Kelvin. So in this illustration here, this would be the valence band. There should be other energy bands below this one, but they would be fully occupied as well. The conduction band, on the other hand, is the lowest energy band, which is unoccupied or partially occupied at 0 K. Okay, so this would be the conduction band, and in insulators and semiconductors, it would be completely empty of electrons at 0 K. For metals, it could be partially filled. And the conduction band is the band which plays an important role in the conduction of electricity, because it is electrons which are situated in the conduction band which can move freely inside the solid or moves when subjected to an electric field, and thus be used to conduct electricity. Let's start talking about metals. Metals have a completely filled valence band and a half-filled or partially filled conduction. So looking at this picture here, this is what we have, right? The fully filled valence band and a partially filled conduction band. It might be that you have two bands here which overlap, but in either case, as you can see, so these are the lines represent the occupied states. The electrons do not have to overcome the entire band gap in order to move to the next available level, okay, as would be the case in semiconductors and insulators. So at 0 K, the electrons here would have to overcome the whole energy of the band gap in order to move to the next possible or next available state. In here, in either case, where the bands overlap or you have a band that's partially filled, the electrons right at the top have to acquire a very small amount of energy in order to move to the next state. And this is important because if you apply an external electric field, for example, you would need to supply momentum to the electron in order for it to start to move. Well, here it's much easier for that to happen because the electron can gain a very small amount of energy and momentum and start moving freely or start moving in response to the electric field inside the solid. So this is an important notion here. It does not have to overcome the band gap. It can move to the next available state with much less energy, much more easily. So the conduction band has free states which are readily accessible to the electrons. The electrons can move freely and are not bound to the atoms in the chemical bonds. Okay, so you have the sea of electrons model because of this, because the electrons can access the next or the higher energy states much more easily. As we said, in some cases the conduction band and the valence band overlap, but you have the same effect, which is the fact that the electrons do not have to overcome the band gap. Semiconductors have a completely filled valence band and an empty conduction band at 0 degrees Kelvin. The band gap is usually anywhere from 1 eV, which is a measure of energy, electron volts, to 3 eV. So these values are smaller than the band gaps corresponding to insulators. In insulators, you have much higher band gap energies. Okay, so this illustrates the case of semiconductors. So as we've said, the valence band is occupied and the conduction band is empty at 0K. And as you raise the temperature, some electrons are able to overcome the band gap, but the band gap is somewhat smaller than the band gap for insulators. Okay, so some electrons at room temperature can still overcome this band gap, and therefore at room temperature you will have a few electrons in the conduction band. And if they are able to overcome the band gap due to temperature, okay, vibrational energy, essentially, and they're up here, they can access these next available states as easy as electrons in metals can. So these few electrons which are able to overcome the band gap will be able to move freely inside the solid. But there's a much smaller quantity of these electrons, okay, in semiconductors. That's why the conductivity is much smaller than the conductivity in metals. So at room temperature, a few electrons will have enough energy to overcome the band gap. At 0K, since there's no additional energy, they will all remain in the valence band. These relatively few electrons can be used for the conduction of electrical current. Okay, so you have conductivities smaller than those of metals, which is of the order of 10 to the 6, 10 to the 7 Siemens per meters. In semiconductors, the conductivities can vary between 10 to the minus 6 Siemens per meter up to 10 to the 5th Siemens per meter. So between the conductivities that you get for insulators on one side and for metals on the other side. The electrons that move to the conduction band leave behind holes or vacant states in the valence band. So this is another important information right here. If at 0K you have this band completely occupied and this band completely empty, and you raise the energy to room temperature, a few electrons are going to move up here. But they're going to leave behind the states that they occupied before in the valence band empty. And these unoccupied states correspond to holes, what we call holes. And holes can also be used to conduct electricity because, well, imagine if you have an empty state right here, and right next to it you have an occupied state. Well, the electron from the occupied state can now move to the empty state. And electrons from other occupied state can now move to the state that is now empty. And this can go on. And therefore, one empty state here means that the electrons can suddenly gain momentum or gain energy. And therefore, it is as if the hole or the empty state would be moving throughout the lattice or throughout the solid. Okay, that's why holes can also move. So in addition to being able to move when the electron moves to the conduction band, it leaves behind a hole which can also move inside the solid. And since it has an effective positive charge, it can also be used to conduct electricity. But all of this is possible because the range of band gaps in semiconductors is intermediary. It's not as high as the band gaps in insulators. So insulators have a completely filled valence band and an empty conduction band at 0 Kelvin, just like semiconductors. But the band gap is very large, usually higher than 3 electron volts, okay? Sometimes much larger than that. For example, for silica, it's around 9 eV. So as the band gap becomes higher, or the energy of the band gap becomes higher, fewer electrons can move to the conduction band at room temperature. This means that you have much fewer electrons that are available to conduct electricity as you would expect. And this is why conductivity in insulators is orders of magnitude smaller than the conductivity in semiconductors and metals. So usually the conductivity values is below 10 to the minus 6 Siemens per meter. So you have much larger band gaps. It requires much more energy for an electron in the valence band to move to the conduction band. That's why very few do, and that's why you have very few electrons and as well as holes available for conducting electricity. Okay, so that's why insulator materials do not conduct electricity very well. For photonic and optoelectronic devices, we're going to be much more interested in semiconductor devices or materials than in metals and insulators in general. And just to give a few examples, for germanium, which is a common semiconductor, the energy gap is 0.67 EVs. For silicon, the band gap is 1.1, around 1.1 electron volts. And for gallium arsenide, which is a 3,5 compound semiconductor, which is used a lot in optoelectronic devices, the energy gap is around 1.43 EV.